Okay, this is exam 4 for Physics 101, fall 2015. Solid sphere has a mass of 10 kilograms and a radius of 2 meters. It rolls, has a linear velocity of 2 meters per second. What is the rotational kinetic energy? Okay, well I know that the kinetic energy is 1/2 I omega squared. So I need to know both I and omega. I for a sphere is 2/5 mr squared. I can know that if I look over here at my equation sheet. Look at this table. Here's a thin-walled sphere. Here's a solid sphere. It's 2/5 mr squared. All right, so that's going to be 2/5 times the mass, which is 10 kilograms, times the radius, which is 2 meters squared. 5 cancels there, gives me 2. It's going to be 2 times 2 is 4, times 2 is 2 times 2 is 4 times 4 again, so that's going to be 16 kilogram meters squared. That's my moment of inertia. And then I also want to know, not omega, but I want to know omega. That's going to be equal to V over R. V is, what is V? 2 meters per second divided by the radius, which is 2 meters. So that's 1 meter. Or excuse me, not 1 meter, 1 radian per second. And now I do the kinetic energy. It's 1/2 of 16 times 1 squared. That's 8 times 1. It's going to be 8 joules. Figure skater pulls in her arms to decrease her moment of inertia by a factor of 2. As a result, she spins twice as fast. What has happened to her rotational energy? Well, again, rotational energy is 1/2 I omega squared. This is increased by 2. This is also increased, excuse me, sorry, 1/2 I omega squared. This is decreased by a factor of 1/2. This is increased by a factor of 2. So I get a factor of 1/2 here and a factor of 4 here. So that means it's going to increase by a factor of 2 because 1/2 times 4 is equal to 2. Solid sphere and a hoop and cylinder all have the same mass. Which is the most difficult to spin? Well, a solid sphere has a moment of inertia of 2/5 mr squared. A cylinder, or excuse me, a hoop has mr squared. This is my sphere, my hoop, and then my cylinder is 1/2 mr squared. I get these all off of that equation sheet. They all have the same mass and the same radius, so it's really just a matter of which of these coefficients is the greatest. And of course, for the hoop, my coefficient is 1, so it has the larger moment of inertia. Consider this object has 2 equal length and mass bars, and then the dashed lines show axes of rotation. Which of these describe the moments of inertia for the object? So about which axis of rotation does it have the biggest to smallest moment of inertia? Well, the biggest moment of inertia is going to be about A. I have to pause here for a second. Okay, sorry about that. My pen stopped working for some reason. Anyway, as I was saying, the moment of inertia about this rotation axis is the biggest. It's the biggest because, look, I got all this mass out here at such a big radius, and then I also have this mass. So that's in comparison to, say, this moment of inertia, where I have this mass at a smaller radii. So I have that same mass, but it's just not as a big a radii. And then also, this bar doesn't extend out as far as it does for A. Now, for C, I don't have a very big moment of inertia because, where's my pen? Because I don't, this part of the bar right here doesn't contribute anything to the moment of inertia. And then finally, for part D, I also have a smaller moment of inertia. So A has the biggest, and then B. So let's first just look at those. So that's going to get rid of this one right here. And now I want to get these others. So A is definitely bigger than B. Now, which else is bigger? Is D bigger than C, or is D equal to C, or something else? Now, C here is going to be bigger than the moment inertia about D. And C is bigger because if I look about this axis of rotation, I have this mass which goes out a full length of the bar. Whereas if I go about the other axis of rotation, about D, then my bar only extends out to 1/2 the total length of the bar. So if I go about the axis of rotation at C, it's going to have a bigger moment of inertia. So I is bigger than B, which is bigger than C, which is bigger than D. So B is the right answer. This figure shows a bar 4 meters long. The bar's mass is 3 kilograms. Mass is attached at one end of the bar. Its mass is 2 kilograms. The system rotates at the pivot point as shown. What is the moment of inertia for this system? Okay, well, I have two things I need to do. First, for a bar, it's 1/12 mb squared. That's 1/12 the mass, which is 3 kilograms, times the length. That's 4 meters squared. So that's going to be 3 times 16, that's 48. 1/12 of that is 4.0 kilogram meters squared. All right, but that's not the answer, so E is not the right answer. So because I also have this mass out at a larger radius, and the moment of inertia of that is just going to be mr squared. I treat that like a point mass. That mass is 2 kilograms. It's at a distance of 2 meters. That's squared. 2 times 4 is 8. So I'm looking at 8 plus 4. So D is the right answer for number 5. A bar has a moment of inertia of 4 kilogram meters squared, and it's rotating at 3 revolutions per second. It engages with a flywheel, which has this moment of inertia. After they engage, they both move at the same speed. What is the new speed? So this is a angular momentum. Li is equal to Lf, conservation of angular momentum. Initially, only this bar has angular momentum, so that's going to be I times omega, will equal to I final times omega final. My I initial is 4 kilogram meters squared. My omega initial is 3 revolutions per second. That's going to equal to my I final. Now I'm taking this 4 kilogram meter squared and I'm combining it up with this 8 kilogram meter squared. So I'm going to have a final moment of inertia of 12 kilogram meters squared times omega final. 4 times 3 is 12, so omega final is 1 revolution per second. Notice I didn't have to convert my units here. It was given in revolutions per second. My units carried through to give me the answer in revolutions per second. Okay, here I have a hoop that's rotating around an axis. What is the net torque? Okay, so I have two forces that are providing a torque. I have this force over here, which is causing it to move in a, counterclockwise, so it's going to be a positive torque. And this torque is causing it to move in a clockwise direction, so it's negative torque. So the sum of the torques will be torque 1 minus torque 2. Torque 1 is going to be 30 newtons times the distance from the axis of rotation, or the moment arm. That's 1 meter minus 10 newtons times 1 meter. 30 minus 10, or 20 newton meters. It comes out to be positive, so it's counterclockwise. D is the right answer. Alright, so consider that hoop. After 2 seconds, what is the rod's angular velocity? So I know the torque is 20 newton meters. I also need to know what is the moment of inertia. This is a hoop, so it's mr squared. Let's see, it was 2 kilograms and 1 meter. So that's 2 kilograms, 1 meter squared, 2 kilogram meters squared. That's my moment of inertia. Then I can find my angular acceleration, torque over I. That's going to be 20 over 2, or 10 radians per second squared. And then I'm looking for the angular velocity after 2 seconds. So I say omega equals omega naught plus alpha t. I'll assume it's 0 initially at rest. So it's going to be 10 radians per second squared times 2 seconds, or 20 radians per second. 8 is D. Okay, what is the net torque on this bar? It's rotating about this point C. Okay, well, this force provides no torque because it's at the axis of rotation. Similarly, this force provides no torque because the angle is 180 and the sine of 180 equals 0. So it's really just this force. I have 20 newtons at 2 meters. Torque is Fr sine theta. 20 newtons, 2 meters. Sine of theta, sine of 90 degrees there, so it's 40 Newton meters. Let's ask ourselves, is this positive or negative? Well, this force causes the object to move in a clockwise direction, so it's going to be negative, in fact. So 40 Newton meters clockwise. This figure shows wrenches and an applied force, which is represented by the arrow, to rank the torque from greatest to least torque. So let's see. I have two wrenches here. One has a big force that appears to be about twice this force, but the moment arm for this one is about twice the moment arm for this one. So these two, remember torque is F times R sine theta. For both of these, theta is 90, so I'll just leave that off. One of them has a bigger force but a smaller moment arm. The other one has a smaller force but a bigger moment arm. So D and C are going to be approximately equal. So I can just stop right there and say that B is the right answer. But I can continue on. Both of these have a torque that is bigger than this one, and this one has a torque that is bigger than A. I can compare D and B more readily because they have the same length moment arm, and since I have the bigger force here, the torque on wrench D is bigger than the torque on wrench B. All right, because it has a bigger force acting across the same moment arm. And then A is the smallest of all because I only have a component of the force that's actually causing any torque at all. So it has the smallest torque of all. So B is the right answer for 10. Rectangular boat is 2 by 1 meters. To what depth is the boat submerged if it has a mass of 500 kilograms? So here, my buoyant force is going to equal my weight. Right, because I have this boat, I have a couple forces that are acting on it. I have the weight of the boat, and I have the buoyant force. In order for this thing to float, it has to be equal. So my buoyant force will have a value equal to M, which is 500 kilograms, times G, which is 10 meters per second squared. So my buoyant force has to equal 5,000 newtons. Right, now I further know that my buoyant force is equal to the density of the fluid times the volume of the object, or in this case, not the volume of the object, but the submerged volume of the object, because it's not completely submerged, times G. So that's going to be, let's see, I have water, we'll assume it's water, kilograms per meter cubed. That's the density of water, you can get that on the equation sheet, times the volume of the object, times 10. This is going to all equal 5,000. And then if I solve for the volume of the object, that's 5,000 over 1,000 times 10, or 10,000. That's equal to 0.5 cubic meters. Okay, but I want to know actually what is the depth. So I say 0.5 cubic meters equals to the volume of the boat. 2 meters times 1 meter times the depth. And then I get 0.5 divided by 2, which is going to be 0.25. So number 11 is C. Boat carrying a large chunk of steel is floating on a lake. The chunk is thrown overboard and sinks. What happens to the water level in the lake? The water level will drop. We had a similar question to this, or actually I think it was the same question. But let's say that I have a container and I have a little boat in that container. And in the boat I have steel. I have a block of steel. Here, the steel displaces its own weight in water. So it displaces its weight in water. And because steel is more dense, the weight of water that has the same weight as this steel will have a much greater volume. So in this case, the steel displaces a pretty big volume because it's so dense. Whereas if I put the steel on the bottom, if I get it out of the lake, actually what's going to happen here is the boat is going to rise and the water level will drop. So now the steel displaces its own volume in water. And its own volume is quite a bit less than the amount of water that it displaces in the first scenario, when it's actually in the boat, when it's displacing its own weight's worth of water. Okay, so the answer there for 12 is B. A swift flame blows across the top of a chimney. What happens as the smoke rising inside the chimney? The smoke will rise more quickly. If I imagine my chimney here, I have smoke coming up. I have a wind that's going here. Here I have a high velocity, low pressure wind. That's from Bernoulli's principle. So if I have a low pressure here, that means I have a high pressure or a higher pressure here that will force that smoke up more quickly. Bernoulli's principle is based on energy. Energy is conserved in a flowing ideal fluid. These other things are true, but they're for other things. So this is Pascal's, for example. This is Archimedes. This is just not true because we know Pascal's principle doesn't predict that. And then this is a continuity equation. So number 14 is D. Water flows through a pipe. Pressure is 2,000 pascals, and the water flows at that speed. It enters a narrower pipe, so its speed is 2 meters per second. So actually, it gets half as big. The pipe, the area decreases by half. What is the pressure in the second section of pipe? Okay, so this is Bernoulli's principle. P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Remember, we also had this rho GH term, but I'm leaving that off because the height of the fluid is not changing. But if the height of the fluid was changing, I would have to include that term. Okay, so I'm looking for P2, 2,000 equals or plus 1/2 thousand 1 squared equals P2 2 squared. And I solved this for P2. This is 2,500 minus, this is 500 times 4 minus 2,000 equals P2. So P2 is at 500. So 15 is C. Which fills a larger volume, 100 kilograms of gold or 100 kilograms of lead? Well, gosh, let's look on our equation sheet. Let's see, gold is 19,300, lead is 10,500. So gold is quite a bit more dense, about twice as dense as lead. So the less dense object will fill a greater volume. This is our mass over volume. I have the same mass. If V is smaller, that means if V is smaller, that means rho goes up. So the, I'm sorry, said that backwards. If V is big, because that's what I'm looking for, a big volume, that means rho goes down. So I'm looking for the less dense, which is lead here. So 16 is B. 17 is a hydraulic jack. Actually, this is a device that's used to crush rocks and stuff. I have an input force, 25 newtons on the left, an input area of 0.008, and then I have an output area of 0.024, and I want to know what is the force exerted by the right piston. Look, I don't have to write anything. I will in just a second, but look, my area goes from 0.008 to 0.024. It is increased by a factor of 3. So I get that bigger area by a factor of 3. That means I'm going to get a bigger force by a factor of 3. So I can tell you right off that the answer would be 75 newtons. But let's just write this out by Pascal's principle. F1 over A1 equals F2 over A2. Remember, this just says that any pressure that I feel inside this fluid, I feel everywhere, any change in pressure. And so whatever pressure I have over here, I will also have over here. I had 25 newtons over 0.008 equals F2 over it was 0.024. If I solve this, I can cross multiply and divide by 0.008. That's equal to 75. Manometer is measuring pressure. The known pressure here is 1 atmosphere. Watch your SI units now. The height of the column is 0.5 meters. The liquid in the mercury is mercury. The density of mercury is 13,600. That's on your equation sheet. What is the pressure P? So first of all, I need to know if P is equal to P naught plus or minus rho GH. Which is it plus or minus? Well, here P is less than P naught. So that means I'm not going to use the positive, I'll use the negative. So it's P naught minus rho GH. P naught is 1 atmosphere. That's 1 times 10 to the 5th pascals minus 13,600 times 10 times 0.5. So it's 100,000 times 5 times 13,600 minus 68,000. That's 32,000, but that's equal to 0.32 atmospheres. So A is the right answer, number 18. Be careful with your units. When you're doing this, you have to have it in SI units because you have other things in SI units here, here, and here. So your pressures also have to be in SI units to make them consistent. Put a straw over a glass of water and place your finger over the top so no air can get in or out. You find that it retains some liquid. How does the air pressure in the upper part compare to the atmospheric pressure? Okay, well, I have a lower pressure here because if I didn't, it would. If this pressure was bigger, it would force the water out. But that's not what's happening. So I know that this is the lower pressure and that PA is bigger than P. So C is the right answer for number 19. Which of these is considered a fluid? A fluid is anything that flows. 2 and 3. D. Person's femur is about 0.5 meters long, has a cross-sectional area. Femur can supposedly support about 30 times the typical human weight. How much will the femur change its length if it's supporting 2,000 newtons? 2,000 newtons is about 30 times a person's weight. If you weigh 700 newtons, 30 times that is about 2,000. So let's see, this is a stress and strain. F over A equals I delta L over L. F is 2,000. A is this 6.2 times 10 to the minus 4. If we look on our equation sheet, we can find the bone Young's modulus 1.8 times 10 to the 10th pascals. And delta L is what we're looking for, and it's originally about 0.5 meters. So we're looking for delta L, 2,000 divided by, get about 3.2 million divided by 1.8 e to the 10 times 0.5. All right, I get 9 times 10 to the minus 5. So here delta L is, it's actually 8.96, but 9 times 10 to the minus 5 meters. So not very much. So 21 is B. Ideal gas is confined to a container without constant volume. The number of moles is constant. By what factor will the pressure change if the absolute temperature triples? So PV is nRT. If this triples, what happens to the pressure with all things else constant? They have a linear relationship, so linear direct relationship. So B is the right answer. A 2-liter container contains half a mole of an ideal gas at a pressure of 12.5 atmospheres. What is the gas temperature? Okay, you have to be careful with your units here. First of all, 2 liters, that's not the SI unit for volume. You need to change it. So here I have PV equals nRT. So my volume is going to be 0.002 cubic meters because it's 2 liters. Also, I have 12.5 atmospheres, but that's going to be 12.5 times 10 to the 5th because 1 atmosphere is 1 times 10 to the 5th. N is 0.5. It contains half a mole. R is 8.314. What's that? Joules per mole Kelvin. And then I'm looking for T. So 600. I get 601 here. I'll come back and take a look at this, but B is the right answer. It might change it for your test. I think it actually is 601, but I'll have to double check that. So 23. All right. A long steel beam has a length of 25 meters on a cold day with a temperature. What is the length of the beam on a hot day? Okay, so delta L is equal to L naught alpha delta T. This is linear expansion. I'm looking for delta L. L naught is 25 meters. Alpha for steel. Go back to my equation sheet. Alpha for steel is 11 times 10 to the minus 6. And delta T is going from 0 to 40, so it's 40 degrees Celsius. That's going to be 25. We get 0.011, so the new length is going to be 25.011. What happens to the moment of inertia when a steel disc is heated? Well, when a steel disc is heated, it gets bigger. Right, so the radius gets bigger, the mass stays the same, so the moment of inertia will increase. What describes the relationship between two systems in thermal equilibrium? That means no net energy is exchanged. You could also say they have the same temperature, but there's no exchange of energy between the two because they're in thermal equilibrium. 88 degrees Fahrenheit is how many degrees Celsius? Well, it's about 31 degrees Celsius. If you want to do this for sure, you can use the equation on the equation sheet, but you need to know sort of these basic temperatures and how they transfer. And which following properties can be used to measure temperature? Length of a solid? Yes. Volume of a gas? Yes. The color of a glowing object? Yes, like with stars. So D is the right answer. All right.